Ok. Boa tarde a todos. Hoje é sexta-feira, dia 23 de julho, e é meu prazer dar boas-vindas a vocês à palestra do colóquio de hoje. So, let me switch to English, because otherwise the speaker will not understand. So, the speaker today is Professor Patrick Johnstone, and Professor Michael from our department helped me to do the invitation, so I'm going to push the session to him so that he can share the session. Thank you, Michael. Thank you, Patrick. Feel free. The stage is yours.
Okay, Antonio, thank you very much for the opportunity once again to bring optimization people here at our colloquium. It's my great pleasure to introduce our speaker today, Dr. Patrick Johnstone from the Brookhaven National Lab in the United States. He finished his PhD 4 years ago, so he's very young, as you can see. And after that, he moved to Rutgers when he hosted a postdoc position under the supervision of Professor Jonathan Eckstein. And he has been involved in different topics in convex optimization, operator splitting, and related applications in machine learning and AI. So Patrick, thank you very much for accepting our invitation. It's a great pleasure to see you here.
Thank you, Maicon. Thank you, Antonio, for the introduction, the invitation. Hello, everyone. So Brookhaven, if you're not familiar, Brookhaven National Lab is based in New York State. It's on Long Island, and I actually live in New Jersey, though. So I've been working remotely since September last year when I started at BNL. So this is joint work with my former postdoc advisor, Jonathan Eckstein, who's at Rutgers, and 2 of my colleagues from BNL, Thomas Flynn and Chin Jae. So this work we began, I think, around January of this year, and we've just submitted a conference paper last month, so it's a good chance to share it with you all. So to give you some overview on this work is to do with an algorithm called projective splitting. Now, this was invented by Jonathan and Bernard Svider in 2008. Now, Bernard Svider is actually based in Brazil, so some of you may or may not be familiar with him. I believe he was Maicon's PhD advisor. So this is a very interesting algorithm for optimization problems, solving monotone inclusions, variational inequalities, and it's really a meta algorithm, meaning that it sort of covers many different special cases, and it's been developed by different people over the past 12 or 13 years. I've worked on it previously when I was at Rutgers and still working on it today. Now, the main contribution of this work is a stochastic version of the algorithm, which is a first stochastic version. And if you're familiar with machine learning, very hot topic, there's an algorithm called SGD, Stochastic Gradient Descent, which is useful for a number of reasons. The main thing about it's useful is that by using a stochastic gradient, you don't need to process an entire data set at one time. You can kind of approximate the gradients by just taking a sort of sample of a data set, and then that's much more efficient than using going through the entire data set. So it's very useful for optimization algorithms to be able to use these stochastic gradients. So this was the first version of projective splitting, as far as I know, that can use this stochastic oracle. Now, the main selling point of the algorithm is its ability to handle constraints and what are called regularizers, and we'll get into that as we go along. The main application I'm going to discuss today is saddle point problems. This is sort of a game, a min-max game, which is becoming more and more popular in machine learning in something called adversarial training. There are other applications of projective splitting, but I chose to focus on this particular application because it's kind of a hot topic. So let me continue. So just the roadmap for the talk today. The first thing I'm going to discuss is just a few different applications in machine learning of saddle point problems or min-max games. So this is something I wanted to just try to advertise for you, is how these are now more and more important in machine learning, solving games between players rather than traditional minimization problems. Then we're going to go through sort of the optimality conditions for min-max games and some of the algorithms you might want to use to solve them. Then we're going to discuss regularizers and constraints, what that means in the context of machine learning, and finally get to the main contribution here, which is this stochastic version of projective splitting. So just to set the scene, in machine learning, I'm from an optimization background, and if you're working at the interface of machine learning optimization, you are mostly concerned with this empirical risk minimization problem. So in machine learning, we have a data set of endpoints, and we're trying to find a model that fits the data in some sense. And normally how people phrase this is by trying to minimize this objective. And this is called the empirical risk minimization problem. So you take a sum over the data points, and you choose a loss function, and you just try to find the model that fits the data as well as possible by minimizing this loss. So this is an empirical risk minimization problem. So the model is parameterized by some vector of parameters. This is you can think of it like the parameters of a neural network, or the coefficients in a regression problem, a logistic regression, or least squares regression, and so on. Now, there's kind of this is the traditional way people working in optimization would look at this problem, but there's also a new sort of type of model which is becoming more and more popular over the past 10 years or so. And this is a saddle point or min-max game between two players. So rather than having a single objective you're trying to minimize, you actually have two players competing against each other. So you have an objective, and one player, theta, is trying to minimize this objective, while simultaneously another player is trying to maximize this objective. So they're kind of competing with each other. And this is actually a more tricky problem to solve. So if you think about one, as I mentioned, there's this method SGD, Stochastic Gradient Descent, which can be used to solve this type of problem pretty effectively, both in theory and in practice. On the other hand, if you try to extend SGD to this problem, then it doesn't work so well. So there's no really equivalent, very simple first order or gradient-based method to solve two, unlike one. So two is a sort of more tricky problem than one. And so you have to think more carefully about what sort of algorithm to use to solve problem two. And so that's sort of the setting, the sort of main problem we're concerned with. Now, I'm going to go through three different applications of this in machine learning. This is not my work, but these are just papers that I'm familiar with, just to sort of motivate looking at these problems. The first is GANS, which is generative adversarial networks. This is probably the work that kicked off these saddle point problems in machine learning. Very famous and effective. The second is privacy preserving ML or private ML, and the third is robust machine learning. Okay, so let's start with GANS, which some of you may be familiar with, but it's really an approach to what's called a generative model in machine learning, meaning we want to be able to generate samples from some distribution. So you can think of it like you want to be able to sample images that look realistic, that look real. And so the way that this is done is by having a generator which is input just a noise vector, W, and would like to output a fake looking sample, usually an image. That's the main application, but it can be used to generate samples from any domain. And it's parameterized by phi. Again, these are usually a neural network, but it could be any model. So the goal here is to have G generate these images that are fake but actually look realistic. And the way that we achieve this is by having this game between a generator and a discriminator. The discriminator's goal is to pick out if it's a real or a fake image. So it will be input an image and will output a probability that it's a real image. So again, it's parameterized by theta. And so this min-max game here, if you look at it from the point of view of theta, is trying to maximize this objective. And so the first term, we have some large data set that we're using to sort of approximate the true distribution of real images, and X is input to that, and we're trying to maximize this, which means we're trying to put a 1 here when we see real data. On the other hand, when the generator is input to the discriminator, ideally it would like to sort of put a 0 here, so correctly classify either this fake as fake data, a fake image. Now, on the other hand, the discriminator is trying to minimize this, so it's sort of in a competition, it has the opposite goal to the discriminator. And so this is sort of a saddle point game, a min-max game. And these are sort of, the sort of goal here is that once you reach an equilibrium, hopefully the generator is generating very realistic images and the discriminator can't tell the difference. But these are known to have convergence issues. So this is kind of known to be a difficult saddle point problem to solve. These are very non-linear, non-convex types of problems. So, okay, that's the sort of first application. The second application I wanted to discuss was privacy, or adversarial privacy. So in this problem, we have a sort of data set. You can think of it like a data set of pairs of variables, so X and Y. And so what you really want is you want to take the data set and privatize the private variables. So Y are these variables that are sensitive information. You don't want people to be able to figure out why. So the idea is to come up with some mapping that takes in the pair of data and then privatizes it, meaning that if you tried to work out Y given X hat, that would be a difficult prediction problem or classification problem. So this is the mutual information is small, the correlation is small between X hat and Y. But at the same time, you still want this to be a useful compression of the data set, or useful privatization, embedding. So you want the X hat to actually tell you something useful about X, the rest of the data. So the mutual information between X hat and X is large, or the correlation. So there are many different approaches to privacy, things like differential privacy, but this in this paper is an approach based on adversarial privacy. And the way that this works is, again, to set up a min-max game. The privatizer is trying to do what we want, to privatize the data, and an adversary which is trying to guess the sort of private variable. So it's input X hat, which is this privatized version, and it's trying to get back the sort of sensitive data. So it's trying to estimate Y from the input X hat. So again, we set up a min-max game here, and from the point of view of the adversary, it's trying to minimize this. So it's trying to pick a very, a model which fits X hat to Y. So it's minimizing some loss here, like least squares loss or some other loss. And on the other hand, the privatizer is trying to make it do poorly. So it's maximizing. It's trying to come up with a model that confuses the adversary. And the privatizer is not allowed to do whatever it wants. If it could do whatever it wants, it would just output zeros or output a random number, and then there'd be no way that the adversary could work out the private data. But it's controlled by a constraint, so that it can't just do whatever it wants. It has to satisfy this distortion constraint, saying that it's actually giving a good estimate of the original data X. So this is sort of a saddle point game here with a constraint. Okay. All right, so let's look at the third application. And this is an application called robust machine learning. And if you go back to the empirical risk problem that we discussed earlier, remember this is a sum over all the data when we have some loss that we're trying to minimize. We can think of this as an expectation, and the expectation is with respect to the empirical distribution, p hat. So it's just a sum of delta spikes at each data point. And when you think about it, if you know about machine learning, you know that this is not actually what we care about. We don't really care about performance on the training data. We don't want our model to just fit the training data. We're just using the training data as a sort of approximation to the real unknown distribution. We want our model to do well on a generalization problem, i.e. you give it a new data point and it performs well on that data point. So it's, if it's an image classification, you give it a new image and it can predict it as a cat accurately. And another issue with this is that what often happens in practice is that as you go from training to deployment, the distribution changes. So the training data is not necessarily reflecting what happens when you deploy the classifier or the model. So this is, of course, very problematic in something like a self-driving car, the training data is never going to perfectly match what happens in reality. If there's something like a change in weather, if it's snowing rather than sunny, then this can affect the performance a lot. So one approach to making models robust to these shifts is to change the problem to a min-max problem. And what we're doing here is saying that, well, the unknown distribution, we're going to allow that to vary. And this is a ball surrounded by the empirical distribution. So you think of it as just a ball of radius delta. So p hat n is the empirical distribution. We're saying, let's let the distribution vary up to some radius delta. And we're going to look for a model that does well, even in the worst case. So even if I allow that distribution to vary within this ball, we have some model that still does well in the worst case and does the best in this worst case sense. And this ball is usually the Wasserstein metric. And so this is again a saddle point problem, but this thing here is kind of tricky because it's infinite dimensional, right? This is a distribution, infinite dimensional object. So this, as it's written, looks pretty ugly to solve. However, there are ways to kind of reduce this to a finite dimensional problem, which I won't go into here, but you can in some cases, make a finite dimensional problem as a way to solve this. Okay, so that's the three sort of applications I wanted to go through. So let's get into the sort of optimality conditions and how we actually might solve these games. Okay, so if you just look at the picture of what a saddle point problem is in the simplest case, one-dimensional problems, you can sort of convince yourself that a saddle point is really an equilibrium or a Nash equilibrium of the problem. That is, we find a pair of strategies such that theta star is a minimizer and at the same time phi star is a maximizer. And one way this is often phrased is that neither player has any incentive to unilaterally deviate, to unilaterally change its strategy. Unilaterally just means to do it on its own, without cooperating with the other player. So this is really what we're looking for, is this pair of strategies or vectors that satisfies these two optimality conditions. Okay, so if you want to minimize a function or maximize a function, then there are these first order necessary conditions from calculus. You take a gradient. So we're assuming this f is a differentiable function, so we can compute a gradient with respect to either variable. So then the first order conditions are that the gradient is equal to 0 for both with respect to theta and phi. And of course, this is necessary, not necessarily sufficient, meaning that this is also a condition for a maximum point, a minimum point, anything, not just a saddle point. If the function is convex concave, f is convex in theta and concave in phi, then this becomes a sufficient condition. So that's kind of a nice thing if you have a convex concave f. Now, one thing that will be useful is to write this condition, the first order condition, as just one vector. So you just kind of stack the two gradients on top of each other. And so we're really looking for the zeros of this pseudo-gradient. This vector is called the pseudo-gradient. And there's a good reason we put a minus sign here, which I'll get to in the next slide. So basically, we're looking for the zeros of this operator B, which is the pseudo-gradient. So why do we put the minus sign here? Well, there's a good reason for that, and that's in order to make this operator what's called monotone. And that basically means that it satisfies this condition, which is this is an inner product or a dot product, and we want this to always be non-negative. And monotonicity is a really important property. It's sort of in the one-dimensional case. If B was just a one-dimensional function, then it would just be saying that it's non-decreasing or basically increasing. Now, it's sort of similar to convexity for this pseudo-gradient. It's a really key property. If you're familiar with convex optimization, you'll know that if the function's convex, we have some hope of being able to solve it, to minimize it. It's a similar thing here for a monotone operator. If it's monotone, we have a chance of being able to compute these zeros. If it's non-monotone, you can think of it as sort of wiggling all over the place, then it's much more difficult to find, certainly, a zero. The zero might not be unique, all sorts of things can happen. And so that's, so this is the problem. We're looking for the zeros of a monotone operator. We're going to use Z as sort of the tuple of theta and phi. So this sort of, makes us think about what sort of algorithm could we use to solve this. So let's just think of it in the one-dimensional case. You want to come up with an iterative method. A simple thing to do would be is this update here. Like if you're in the part of the graph where B is positive, you move to the left. If you're on the part of the graph where B is negative, you move to the right. Okay, so that's just this update here. And if you unpack what this means in terms of B, so remember B has this definition, then this becomes what's called the gradient descent-ascent method, or GDA. And what that is just in the theta variable, which we're trying to minimize, we take a descent step. So we compute the gradient and move in the negative gradient direction. And then we do at the same time an ascent step. So for phi, which we're trying to maximize, we move in the positive gradient direction. And so we just iterate this process, and alpha is just a positive step size that we have to choose. And this is a very intuitive method. It's sort of, if you were thinking about this problem from first principles, you'd probably come up with this method to solve this problem. And I think if you were lucky enough to doing research 60 years ago in the 50s or 40s, you'd probably, there's a lot more low-hanging fruit. You'd probably come up with GDA. And so this is a very intuitive method. It's very popular, but it has some issues. The main issue is that there are lots of cases where it doesn't work. So it's a little too simple. So this is a very simple counter example that shows when GDA fails. So this is a saddle point problem. Where we've just got real numbers here. Theta times phi is the objective. And this actually has an equilibrium at the origin. And if you work out the pseudo-gradient just by computing, gradient respect to theta stacked on top of minus gradient respect to phi, it becomes this 90 degrees clockwise rotation operation. Now, this is a very well-known counterexample. And what happens when you run GDA, this is an experiment I ran, it just spirals out to infinity. So it doesn't converge. The solution is at the origin here, and this thing just diverges out to infinity. And the issue here is that these black arrows are telling you the direction the algorithm will move in, this vector field, the sort of the minus pseudo gradient. And this happens for any small steps, any step size you choose, because the pseudo gradient is sort of orthogonal to the direction to the solution. Solution's at the origin, and because you're doing a rotation, the direction the algorithm moves in is perpendicular or orthogonal to that direction. So this is not going to work on this problem. And in general, for GDA to work, you need some stronger assumption on the problem. Than this, you need strong convexity or something more restrictive. Now, the version of GDA that people often use is called the alternating version. So this is slightly more intuitive in the sense that for the second update of phi, we actually use the latest information that we have. So we update theta k to get theta k plus 1, and then we use that to get our next iterative for phi k plus 1. And this also fails, but not quite as spectacularly. So this just ends up rotating around and doesn't diverge, but it also never converges. But this method GDA is still very popular, and it's particularly machine learning for GANs and things like that. It's still a very common method people try as a kind of heuristic. And many people have modified the method or done little tweaks to try to make it perform better. But another approach is to sort of just ignore GDA. If you wanted to come up with a method for saddle points, look for a different approach. And this was done like over 40 years ago to come up with the Extragradient Method. In 1977, this method is actually guaranteed to converge on this counterexample. And this method is a little bit more complicated than GDA in that you do two pseudo-gradient steps at each iteration. It's called, the reason it's called extragradient is it's based on this extrapolation point. So you compute z hat extrapolated from ck, and then you just use that as a second point to compute the pseudo-gradient. And if you run this on the same problem, then this will actually converge to the origin. So this is sort of a nice result. And this method is pretty well known in optimization, math programming, but not that well known in machine learning. Okay, so one other thing that people really care about in machine learning, as I mentioned a couple of times, is doing stochastic gradients. So let's just see, exactly why that's important. So if we go back to the GAN objective, generative adversarial network, you have this sum over the entire data set that appears as this sort of first term here. So to compute a gradient here would involve going through every point in the data set and computing this gradient and then summing them up. So some data sets in machine learning might have like 1 million samples or 10 million samples. So this is really prohibitive to do this gradient exactly. So what people much prefer to do is to take a stochastic estimate, what's called a mini batch estimate. You just pick a small number of samples, small number of points, and then compute this approximation. So B might be, say, 100 or 1,000 points or 50, and then you use that as the sort of approximation to the full gradient. So this will be, if B is chosen randomly, this is sort of unbiased. It has the right mean, but it will have some variance. So now there are versions of the Extragradient method that can work with this kind of stochastic estimator. Okay, let's continue. This is a different sort of a change of topics to how to use regularizers and constraints in machine learning and these sorts of problems. Okay. All right. So constrained optimization. So these problems look like this. So this is not a game, so you can forget about min-max games, saddle points. This is just a minimization. We just have a function we're trying to minimize, and we have what's called a constraint, meaning that we want to find a solution that's in C. C is just a set. So it's a set in the domain of F, typically closed and convex, but not necessarily. And if you wanted to solve this type of problem, there are different things you could use, but if F is differentiable, a simple thing to do is called the projected gradient method. So you're just iterating, you take a gradient descent step, so rho again is a step size, just a positive constant. But if you do that, that's not taking into account the constraints. So the way people take into account the constraint is by projecting onto the set C. So taking a gradient descent step here and then projecting back onto the set C. And just iterating that process, this is known to converge to, under reasonable assumptions on F and the set C. And of course, this will only work if you can actually project onto this set. So the C has to have a projection that you can compute in order for this whole process to be, something you could use. Now, a related thing that people do in machine learning is the use of regularizers. And so this means we start with a minimization problem, this time without a constraint, and we add an additional term to the objective called a regularizer. This is used for a variety of reasons. In particular, people use it to promote sparse solutions, that is, solutions that have only a small number of non-zeros. There's a whole literature on using regularizers to reduce the overfitting problem in machine learning. So examples, the L1 norm is often used to promote a sparse solution. This is the Euclid norm, which if your variable is a matrix, this is used to obtain a low rank solution. Now, from an algorithm point of view, the issue here is that these regularizers are usually non-smooth, non-differentiable. And so if they were differentiable, we could handle this just using gradients as we normally do. But the issue here is the non-smoothness. Now, the way that I like to think about constraints and regularizers is that they're really the same. So this sort of shows this equivalence between regularizers and constraints, which is sort of well known in optimization, but I think could be better known outside. And that's really that you can sort of make them equivalent by just using what's called the indicator function. So you have some constraint C that you'd like to impose on the problem. Well, this is equivalent to using this indicator function format. So you have a function R, which is just equal to 0 on the set C, and then plus infinity outside of the set C. So you can imagine if you added this in the objective, whenever the iterate goes outside of C, you have some candidate point. This Rx blows up to plus infinity. And so by adding this to the objective, you're really effectively constraining the problem to stay on the set C. And so this is really showing that you can think of constraints as being equivalent to just a special type of regularizer. Now, there's another benefit to doing this, which is that it gives a way to generalize projected gradient descent to problems that are regularized. And this is called the Proximal Gradient Method. So with this method, we're trying to solve 3. We have a function f plus another function r. And this is r is just for now, we'll assume non-smooth, non-differentiable. And the way that it does this is very similar to projected gradient method. You take a gradient descent step, but now it uses this proximal operator, prox. And this prox is defined here, and it's basically a sort of sub-problem that you have to solve at each iteration. And it generalizes projection. So if you plug in 4, the indicator function here, into this prox update, you get back a projection. You're projecting onto the set C. And so that's one of the benefits of thinking of constraints and regularizers is the same as you get you can think of this new method for solving regularized problems. Now, what is the point of all of this anyway? Like, why is this useful? Well, we have a non-smooth problem here because of R. But if you use this proximal operator, convergence is basically the same as if the problem was a smooth objective. So the benefit of this is speed. Proximal operators get you, using this proximal update, will get you a faster method. And there are other ways to deal with non-differentiable objectives, things like subgradients. But if you can use the proximal operator, you'll get better performance in general. Now, the big caveat here is that you need to be able to compute this proximal operator. You need to be able to compute this thing. And you do that at every iteration. So this has to be relatively cheap to compute to make this a sort of worthwhile method. But the good thing is that there are many regularizers people use that have cheap proximal operators. So the canonical or famous example is the L1 norm, which I mentioned is used for finding sparse solutions. If you plug the L1 norm in here, you can compute that in a closed form way. Okay, so let's get back to games, so min-max games. So you can use regularizers in games as well, or constraints. And typically, by convention, people do this on each variable separately. So we're just adding one regularizer for theta and one regularizer for phi. And note that we use the minus sign here, again, just by convention, because this is a maximization problem for phi. So if you're going to use a norm like the L1 norm, it would make sense to use a minus sign here. And the question is how to deal with this. What sort of algorithms would you use for this? And the main issue, again, is the non-smoothness of the regularizers, or non-differentiability. So this is, dealing with this for one regularizer has been done, solved in about 20 years ago in Seng's method. Now, you don't have to worry about all the details of the updates, but just notice that the main features here is that it's using the proximal operators of each regularizer. So we need to be able to evaluate those. And it's also using this extrapolation point idea from the Extragradient method. And actually, this method is a generalization of the Extragradient. Extragradient is a special case. And the one issue here is that it's using the deterministic gradients, and that's something we'll address with our method in a couple of slides. But before we get there, one sort of natural thing to ask about, or at least to think about, is what happens if we have multiple regularizers or multiple constraints. So if you imagine you might have a problem. You think the solution should satisfy not just one constraint, but say a few different constraints. And this is equivalent to using an intersection of constraints or a sum of the indicator functions. So it's a natural thing to want to be able to do. For regularizers, it's also equivalent to using sort of wanting a solution that satisfies several different structural requirements. For example, you might want a solution that's both sparse and low rank at the same time. And so this is a natural thing to want to be able to do. And again, algorithmically, what's the issue here is that we have non-smoothness here. We have non-differentiability in these terms. And there's even more than that. If we think of it in terms of these proximal methods, we want methods that are called full splitting. At least this is something that people have looked into in the literatures. These are sort of nice methods because they compute the proximal operators of each function separately. So it's kind of a sort of beautiful thing, an aesthetically nice thing for a method to do, and it has kind of nice properties as well. Because if you think about these proximal operators, even if the prox of each individual term is available, it may be difficult to compute the prox of the sum. So if you have the L1 norm and the L2 norm, you know that each of these proxes, not necessarily easy to compute the prox of the sum from using those two proxes. And you can think of this also in terms of projection. You may have a projection onto one set and a projection onto another, but using those together to compute the intersection is there's not necessarily a closed form formula for doing that. There's no obvious way to combine them together. There may be a way to get it from first principles, but there's no sort of general formula that will always work. So what we really want is methods that can utilize each individual prox and doesn't need to utilize the prox of the sum, which might not be available. And these are called full splitting methods. So these are sort of desirable, people trying to design such methods. And we can finally get to the sort of main open problem of this work, which is to do this, to have a full splitting method that is a method that uses these individual proximal operators and uses a stochastic oracle for the pseudo-gradient. This sort of, in a way, is motivated this work. And as far as I know, there weren't really good answers to that open problem. There were definitely methods in the deterministic case if you want to use pseudo-gradients which are deterministic, but not necessarily stochastic, which, yeah, is sort of a key property for using these for machine learning. Okay, yeah. So, and main contribution of this work is to provide the first such method, and the first full splitting method, that is a method that uses these individual proximal operators of each term here and a stochastic oracle for f. And I put two footnotes here because, of course, the first that I know of, this is a big literature, there may be ones that I'm not aware of. The second caveat here is that this is under standard assumptions. Now, assumptions are somewhat subjective, but there are a couple of other methods that could potentially be considered the first such method. However, they use stronger assumptions than ours. They require increasing the mini batch size, sort of progressively growing the mini batch size, which is not typically done in practice, or they might require stronger assumptions such as strong convexity. And so this is all based on projective splitting. It's a stochastic version of projective splitting, and it includes the extragradient as a method as a special case. So in effect, it makes the extragradient method work when you have all of these additional regularizers and constraints. Okay, so how does the method work? Now, I'm not going to go into all of the details about how the method works, but I'll just give kind of the high-level idea, the intuition behind projective splitting. So let's just imagine that you have a unique solution. So this blue dot is the unique solution to the saddle point problem. Projective splitting is based on constructing separating hyperplanes. So these green lines that separate the sort of current estimate you have from the solution. So if you have a method that can create these separating hyperplanes, then by projecting onto the hyperplane, you sort of get closer, make progress towards the solution. So you can kind of iterate that process, iteratively construct these separating hyperplanes and get sort of closer and closer to a solution, ideally converge. Now, two things may come to mind, the first is, well, I mean, it's one thing to have separating hyperplanes, but they actually have to be good separators. So you can imagine this scenario in the bottom left here where you just sort of stall out. The method doesn't make enough progress and just sort of gets stuck. So these separating hyperplanes actually need to give you a good cut between where you're at and where the solution is. And the second thing that you'd be wondering about is how do you actually get these separators? And there are several different schemes for generating these hyperplanes. This is actually where most of the research has been going on in projective splitting, is how you actually do this. And they're actually splitting schemes. So they're schemes based on proximal operators of each individual term here, and then gradients of f. But they're all deterministic. So the focus of this work was to make that work with a stochastic oracle. Now, if you go to stochastic oracles, that makes things, of course, a lot more tricky. For one thing, when you look at what happens with these hyperplanes, they're no longer separators because of the noise in the gradient. So they might not even separate. They might be pointing in completely wrong direction just by chance. So there's something that you have to deal with in the analysis, and the way that this is dealt with is just by weighting the sort of hyperplane direction by a decaying step size. So we pick a step size, and just rather than projecting onto the hyperplane, we only move in a weighted step in that direction. Now you have to pick the step size to decay at the right rate. If it decays too fast, then you'll never get anywhere. If it decays too slow, then you could diverge because of the noise. So this has to satisfy a sort of rule, decay at the right kind of rate. And then you also have to do a similar kind of decaying step size within the actual updates to get the hyperplane. So this decaying step size is very common in stochastic methods in optimization. So this is sort of the key to making the whole thing work, is using these decaying step size and picking them to sort of decay at the right rates. In terms of the convergence analysis, just to summarize what we proved, we proved that with probability 1, the iterates will converge to a solution. And the analysis is all, the main sort of tool that we use is this stochastic, a total mouthful, but I didn't name this, the stochastic quasi-Fager monotonicity property coming from this paper. And this is sort of the key technique that we use to analyze the method. So in addition to convergence to a solution, we also proved rates for this approximation residual. It's essentially the norm of the pseudo-gradient, which we want to converge to 0. It's a little more complicated than that because of the non-differentiable terms, but this is, you can think of it as the sort of, this is the sort of idea. And all of this is all of these results are in the convex-concave case, when f is convex in theta and concave in phi. In many applications, that doesn't hold, especially GANS and machine learning applications. So the best we've got for the general case is a sort of local analysis, i.e. if the method is initialized close enough to a local equilibrium, then you can prove convergence in that case. But this is sort of the best we've got in that general case. Let's just look quickly at a numerical result. So this problem is going back to the application I discussed on robust machine learning. This is a saddle point problem, and remember, we're looking for a model that fits the data, but we're allowing the distribution to vary within some ball surrounding the solution, surrounding the empirical distribution. And this is actually a convex-concave problem. The specific loss we're using is the logistic regression, and there's a finite dimensional way to write this. So this is just comparing our method in blue. There are two different step sizes we use, the decaying step size and then also a fixed step size that you can use as well. The two blue lines are our method, SPS. And then we're comparing that with 3 different deterministic methods. So the red method is the deterministic projective splitting method, i.e. the sort of previous version, and then Tsang's method and another method called FRB. And so there's 3 different data sets here, and we're measuring this approximation residual versus running time. And at least on 2 of the data sets, we're doing a lot better. These other methods are deterministic. They can't use stochastic oracles, so they have to process every point in the data set to get an update. whereas we can just use sort of mini batches, and that gets us sort of allows us to make faster progress, at least in the early iterations. Okay, so that's pretty much where I'll wrap up. Just in terms of the future work here. So one of the nice things about the analysis is that it also works in a distributed asynchronous setting, meaning that you have multiple computing nodes basically talking to each other, but they don't need to be totally synchronized. So this is kind of something that we could potentially use for large-scale machine learning training when you have sort of things like HPCs, computer clusters, which we have here at BNL, and we can try to run this algorithm in a more distributed fashion. So we have an analysis for that, but we haven't really done experiments yet. A simple thing we could try is an asynchronous version of the Extragradient method. The Extragradient method is a very old method, 40 or so years old, but as far as I know, there haven't really been too many asynchronous versions studied. So we can do that with our analysis, since Extragradient is a special case. And the final thing, a legitimate criticism you might make of this work is who really cares about problems with multiple regularizers and multiple constraints. This might just be kind of a niche thing that not that many people are interested in. Now, you could argue that because there aren't really methods for solving such problems, that's why people just don't have an option. And now with SPS, they could potentially try to add more constraints that might be useful for their problem. So we kind of have to do some digging and find more applications where that could be useful. All right, so that's going to wrap it up. And this is the paper. Thank you all.
Okay. Thank you, Patrick, for your very nice talk. I'm sure that the students enjoyed a lot because you started from the very basics. So yeah. Thank you for taking our time to prepare this talk. Thank you very much. Thank you very much. So I don't know if you have questions or comments so far. I think perhaps Antonio, you can help me to.
Yeah, I don't know where I see the questions, or is that you might have to tell me where I see them if there are any.
I can remove your slides, but maybe you need them. Actually, I do have a question. You talked about this Proximal method, and you have a regularization term. I think you call it alpha, but I'm not quite sure whether you intended to use it constant along the iteration process or to update it during the iterative process.
Right. Let me go back just to clarify.
So you have a constant before a regularization parameter before the regularization term.
Yeah, so that's in the, let me go back. Yeah, so, well, this is one example. This is not actually a constant, this is just a step size. So it doesn't actually appear in the objective. So this is just something the method uses within the updates. And for projective splitting, you do have to make that decay. It has to be the same step size for the gradient that you're using and for the proximal update. Yeah, so that's yeah. Well, for projective splitting, actually, they're not. You don't have to make that step size decay. But so there are two things to address. First of all, this is not like a weight that you use in the objective. It's just a step size, and then depending on the method, you might have to make it decay. Yeah. Mm-hmm. I'm not sure if that answered your question. You might want to. Is that okay?
So, because then you don't. You have a penalization term, but you don't add a weight before this penalization term.
Yeah, I just assumed that it's within the function R, but you could imagine taking it out. Yeah, but I'm just saying that R theta could be, for example, lambda times the norm of theta. Yeah.
Mm-hmm.
Does that? Yeah. So it's just subsumed within R. Yeah.
I'm asking you because usually in regularization theory, the magic lays on the choice of the regularization parameters, so that you find an optimizer that is easy to calculate and it's not very far from the solution that you want to calculate.
Sure. Yeah. So that's absolutely possible within these methods. Yeah. Just put lambda inside the definition of R. Yeah. That's totally fine. Yeah.
Okay. Thank you.
Yeah.
Okay. Well, I have a lot of questions, but some of them very technical because I'm to some extent aware of what is going on in this subject. So, but
yeah.
Regarding the noise, when we talk about stochastic case, the noise, do you have some a priori information about the noise level, or let's say?
Yeah. Basically, it has to be unbiased. So the mean has to be 0. The mean has to be equal. So the mean of the noise is 0. Yeah, and then the variance has to be bounded. So it basically has to be the expectation of the expectation of the norm squared of the variance has to be bounded, and in this case, not uniformly bounded, meaning that the bound can sort of depend on theta, essentially. Yeah. So I don't want to go into the technical details there, but yeah.
Okay, but even in this case, in this scenario, you do need the vanishing step size, the alpha.
The step size has to vanish. Yeah. Yes. So.
So there's no way to avoid this.
Yeah, there's no real way to avoid that if you have noise with sort of non-vanishing variance. Yeah, the step size has to decay. You can use a fixed step size, but basically the step size is fixed at some small level. So you set the number of iterations you're going to run, and you essentially pick the step size to be sort of 1 divided by the number of iterations, or the square root of that. But okay. Yeah, this is kind of unavoidable for any method that uses. There are things like variance reduction, which will allow you to get around that. But variance reduction methods depend more on the structure being a finite sum problem. And then you can potentially get around that. But this is sort of a generic situation where you just have noise. And I'm not aware of many methods that can avoid using a decaying step size. Yeah.
But if you don't know the noise level, then in this picture that you're showing us now, you cannot make sure that the separating hyperplane actually separates the current point from the solution. But if you know the noise level, then you can. You just can control the step size.
No, yeah. You don't need it. The point is you don't need it to be separating. It's not necessary. Because essentially what happens is you're sort of trusting it to a certain extent, but you just have to move it. Because this alpha k is decaying to 0 in the end. You don't need it to be an exact separator. It's sort of just this alpha k is picked in a specific way to sort of cancel out the noise terms that arise. So this comes down to this quasi-phasor monotonicity update. So yeah, it doesn't need to be a separator. That's sort of the key to the analysis. Yeah.
There's a comment arriving.
Mm-hmm. Can you read it out for me? Because I don't know how to get to see the...
Oh, can't you see the screen?
Yeah, I'm not sure. I don't want to give you like the staircase recursion. So can someone read it? Michael, can you read it for me?
Yeah, from Jonathan Eckstein.
Yeah.
You need either vanishing step size or vanishing noise.
Yeah. Pretty much, yeah. And usually vanishing noise is in machine learning, vanishing noise means using batch sizes that sort of grow as you go along. And people don't really use that. So that's kind of a less realistic setting than using a step size that decays. Yeah.
Sure. Another remark? Oh, again, you can't read.
Let me, yeah. I don't know.
Can you see the...
Oh, yeah. Okay. Yeah, they just need to be separating on. Yeah, so you can think of it like that way. So if there's no noise, or the noise is close to 0 to its mean, then this hyperplane would be a separator. That's the key. It has to give you some information about where the solution is, but it can be noisy. So you want to trust the hyperplane to a certain extent, but then also not completely trust it. That's the intuition. Yeah.
Interesting.
Yeah.
Okay.
Yeah.
So, Antonio, I don't know if there are other questions or comments. So thank you, Patrick, for...
No problem. Yeah, I stopped sharing my screen, so maybe I can see the comments now. But yeah, thanks, Maicon.
Well, guys, thank you very much. I think the students are shy today. Usually they do when we have talks in English. So I'd like to thank you both, Michael and Patrick, for coming today and for this very nice talk, Patrick. It was a pleasure. So, and would like to give some final words to our students and to the audience.
Michael or myself?
You, please.
Oh, yeah. Thanks for your time. Hope you're doing well down in Brazil. All the best.
Mm-hmm. Okay, so let me say farewell to the students. Muito bem, obrigado a todos pela apresentação, pela audiência, e nos vemos na próxima sexta-feira, na próxima palestra do colóquio. Muito obrigado a todos, uma boa tarde, bom final de semana e muita saúde.
Tchau, tchau.